guys. Nice to see you. How are you doing? Tired? No? Okay, very good. You are young, you shouldn't be tired. So, we continue our discussion of application of laws of motion. So I don't recall now, like, I don't refresh you again the definition of laws of motion. I think that you already remember it. However, so far we consider some idealistic conditions when we don't have any friction force. Those that we have ideal surfaces which do not create any friction when we slide one object over another. In reality, obviously, it's not the case, and we do have friction. We need to take this into account because it defines the everyday experience of what we have in our life. So let's say we imagine some box placed on the floor, and if we exert some force, which is quite small, depending, of course, on the conditions of the surface and weight, but this small force will not start moving the ball. So this box will remain constant, like steady. Nevertheless, we apply some force. So that looks like some violation of second law of motion, because we know we apply force, we need to get some acceleration. So ma is equal to f, or a is equal to f divided by m. However, it's not happening in reality. So we apply some small force, but the box is staying where it was. No acceleration, no motion. So that is the reason of so-called static friction force. So static friction force is some force which counteracts the driving force up to some maximum level, which cannot be exceeded for static friction force. So let us try to visualize it a bit more clear. So we have some surface, and a box on the surface. So obviously it has some weight, mg, and also it's compensated by reaction of the surface n. So now we exert some force F, but this force does not move the box. And that's because we have some counter force, like static friction force, ST, FST, which compensate the applied force. So if we consider in magnitude, this maximum static friction force will be equal to mu st times n. So mu st is so-called static friction coefficient, and any suggestions what will define the static friction coefficient? Obviously, we have a contact between two surfaces. So here we have contact of both surface with the surface of the floor. Conditions of the surface, the quality of the surface, roughness, that what will define this coefficient mu st, static friction coefficient. Another factor which defines maximum static friction force is the reaction of the supporting surface, and in this case it's n, which is equal to the weight of the box. So there are two parameters, and as you may notice, we are not talking about the area of the contact between box and the supporting surface. So area doesn't matter in this case, only properties of the surface, which is in this parameter embedded in parameter mu st and coefficient and reaction of the supporting surface. So let us see what is happening when we start to increase exerted force F on this box and how static friction force responds. So we can plot such a figure when we have friction force, let's say F versus applied force. Um, Initially, when applied force is smaller than the static friction force maximum value defined by mu st times n, there will be linear dependence. So we increase exerted force, and the same uh, static friction force will be. So it will just compensate applied force. However, it will not continue always, because we know from experience if we push enough, this box will move. So there is a transition between static friction and kinetic friction. So at some point, when there is a transition between these two um, conditions, static and kinetic, it reaches maximum value, and maximum value of um, static friction is equal to mu st times n. It will drop a little bit and then reach saturation. So it will be constant. It will not change with applied force. And that will be mu k times n. And this is F kinetic friction. So you see from here that maximum static friction force is a bit larger than kinetic friction force. So that is because kinetic friction coefficient mu k is a bit smaller than static friction coefficient mu st. Now with direction of friction force, the static friction force is always oriented in opposite direction to applied force. So we have applied force to the right and static friction to the left. Once we have already kinetic friction, means the body already moves slides with respect to the surface, supporting surface, then we can deal for definition of the direction of kinetic friction force with velocity vector. So it's always in opposite direction to velocity vector. So quite straightforward. So this is about interaction of two solid, like two objects with made from solid material, where we have quite clearly defined surfaces of this material. However, there are also cases when we need to consider so-called drag force, and that's force when we have interaction between a solid material immersed in some uh, different environment. So it's not the contact with another solid material, but it moves either in air or in, let's say, some gaseous environment or in liquid environment. So in that case, we call it not friction force, but drag force. So we need to distinguish between two regimes of drag force. So one is low velocity and high velocity. Low velocity when we have um, kind of so-called laminar flow of liquid. Let's say we consider example, we have some solid body in a liquid. And this liquid without any curves and disturbance flows around the object. So this is the regime of small velocity. We don't create any turbulence in the flow of liquid. And drag force can be represented with a quite simple equation. So let's see, this is our object. which is moving in some liquid, and this liquid just flows quite laminarly around this object without any disturbance. So this is the direction of velocity vector. This will be the direction of drag force. So drag force can be determined as minus k times v vector. So that is the equation for drag force. So we see, first of all, that with this minus is always in opposite direction to the velocity vector, and we have linear dependence of drag force on velocity. Now let us say a little bit information about this coefficient, proportionality coefficient k. And here it's quite easy to use this equation, quite straightforward and simple, but there is quite a lot of information hidden here in this coefficient because it takes into account many factors. So first of all, shape of the body, which is moving in liquid, conditions of its surface, that's how it interacts with, like its surface interacts with the flow of water or as a liquid. Then it also takes into account viscosity of the liquid, um, density of the liquid. Since density is a function of temperature, also temperature of the liquid, and so on and so forth. So it's quite complicated picture, which compressed in this coefficient. Once we know it, of course, that's quite an easy task to determine the drag force. So hydrodynamics, aero and hydrodynamics, it's a field of study which systematically investigates such questions and defines these proportionality coefficients for different conditions, because every case is different and you need to do a lot of research in order to get this value. So now let's say if we go to this second mode, when we have high speed, and in that case we start to deal with some turbulence which is created by fast motion of this object in water. So that obviously takes some additional energy to create. So it changes conditions of the interaction between the body with the liquid. If it changes these conditions, and we mentioned that this proportionality coefficient is the parameter which takes this into account, we need to deal now with a different proportionality coefficient, and also dependence on velocity becomes stronger. So for high speed regime, we can write for magnitude of drag force, we can write that it's equal to k prime. It's some new coefficient which takes into account already existence of these disturbances around the body in the liquid, times v squared. So it already depends on velocity in second power, so it's much stronger dependence than the first linear case. Okay, so this is general information about friction forces and drag force. So let us try to consider some examples where we can take this into account. So first, let's come back to our old good friend inclined plane. Consider a box with some mass. So we have mg weight. Here we have some angle theta. We remember from previous discussion that it's convenient for us to introduce a system of coordinates when axis x goes along inclined plane and axis y is perpendicular to inclined plane. Now we can split our weight vector in two components along axis x and axis uh, y. So here will be mg times cosinus theta, and here will be mg times sinus theta. In y direction, we will have reaction of the surface. So we will have n vector here, reaction of the inclined plane. And now we can introduce our static friction. So here will be no, because this theta and this is the angle theta. So the here, if we transfer this here, so this will be in this direction is cosine, and in this direction will be sine. Okay, so now we take into account, we can delete this, we can take into account F static friction, and the question will be at which angle theta this block will start to slide. So imagine that we have first horizontal plane, and here is the mu st, the static friction coefficient between the box and the plane. So we start from horizontal plane, we start to increase this angle theta, and as angle theta increases, this projection of weight on axis x also increases, and at some point this will be larger than static friction and block will start to move. So let us consider first axis y. Along axis y we have n minus mg cosine theta equal to 0. There is nothing happening along axis y. And when this condition will be true, that block starts to slide, when x component of weight will be equal to static friction. So we can write F, maybe like this, mg sinus theta minus or let's say we can put equal to F as T. And static friction force is, we defined it previously, that will be equal to mu st times n. Now we need to define what will be n in terms of weight, mg, and that can be defined from this first equation. So n is equal to mg times cosinus theta. So now we can substitute this instead of n, and we get mg sinus theta equal to mu st times mg times cosine theta. So we cancel out mg and get the following. So it will be sinus theta over cosinus theta. That is tangent theta. And that is equal to mu st. So you see that the angle at which this block will start to slide depends only on a single parameter, which is static friction coefficient. So the conditions of the surface of the block and the inclined plane will define at which angle this block starts to slide. Nothing else matters there. So the weight, the mass of the block is not included into equation. So let us go to another example with some circular motion. We considered circular motion, so you need to remember about centripetal acceleration. And let us consider such an example. So we have some curved road, and some car is moving with some velocity. This is the radius of this circular trajectory. There is some friction coefficient, like static friction coefficient, between tires and the surface of the road, asphalt. So the question will be how fast we can go with this car in order to be able to move safely through this curved trajectory without being without sliding away from the surface of the road. So let us consider this in a bit different projection. So let's take a look on this car from the back. So this is the road. This is the car. We have some weight, mg. We have some reaction of the surface of the road. Since it is motion along a curved trajectory, we have centripetal acceleration, and that means since we consider the car itself, we need to deal with centrifugal force, which kind of pushes it away from the road, from the center of this curvature. And this will be our centrifugal force. And obviously, there should be friction, static friction force, which keeps this car on the road. Otherwise, it would just go away. So this is our FST. Okay, so let's see what we get here. The condition that car stays on the road is FST is equal to FC. Static friction force is equal to centrifugal force. If centrifugal force is larger, the car will be just blown away from the road. What in the left side we have? It will be mu st times n, which is mg. In the right side, can you remind me the expression for centrifugal force? M. That is correct, but here we deal with linear velocity, so in linear v squared divided by r. Exactly. So now we can cancel out this m, and we can express, so in this case, it will not be just some v squared, it will be v maximum, allowed that car will still stay on the road. And then we see that v maximum is equal to square root of mu st times g times r. Okay, so that is the expression for maximum velocity allowed if we go faster. That's not going forward. Imagine a condition which probably, like, definitely everyone wants to avoid, that you experience some driving with very bad weather conditions, and the road is covered with some thin layer of ice, and there is zero static friction between your tires and the surface of the road. Quite critical scenario. And we, in that case, mu st is approaching to 0. So if that is the case, if you substitute here instead of mu st 0, you will get 0. So V maximum will be 0. So from this equation, this particular example means that when you don't have any static friction with the surface of the road, it's impossible to go through this curvature even with very small velocity, because the even if you go very slow, there still be some centrifugal force, and there is nothing to compensate the centrifugal force because there is no static friction, so car will slide away from the road. Any suggestions? Can we do something in such case? Can we modify our system in order to be able to drive through this curvature with condition when mu st is equal to 0? Increase radius. Well, that is reasonable suggestion, because here radius results in the increase of velocity, maximum velocity. But keep in mind, this is 0. Doesn't matter what you do here. If you multiply by 0, it's 0. Yeah. Change tires. Well, change tires, that means, well, first of all, of course, don't forget to change your tires from summer. But that implies that you will have not 0. But assume that someone forgot to change tires and it's icy road and we have actually 0. There is no friction. And believe me, that's really not good experience to have some feeling when your car doesn't react to anything. What you turn the wheel or you press the brake doesn't matter, it just slides. And unfortunately, it happens even on winter tires, so it all depends on the conditions of the road. So, any suggestions? Covering by center. Huh? Covering by center. Covering. Covering what? Sure, but that's all means that we increase in sky. But the condition that we cannot. So this remains 0. Other terms? Rewrite. Well, it doesn't matter what we rewrite. It's just physics. It should work. If this equation work, we cannot rewrite it, but we can make some change in the system and look at this row. How oriented this row? Huh? We can make it symmetrical. Exactly. We can tilt the road, and then there will be some component of the weight of this car which will compensate the centrifugal acceleration. So let's look here. Instead of having this surface horizontal, let's introduce our lovely inclined plane. So this will be some angle theta. This is our car. This car, like tires, they don't experience any friction with the surface. Mu st is equal to 0, so we can neglect with the surface, with the friction. Here we have mg. We can also introduce x and y axis. So in this direction will be projection of weight of the car on axis x. It will be mg times sinus theta. And here will be reaction of the surface and here will be mg times cosine theta. And this direction will be our centrifugal force. So in this case, regardless of the fact that we don't have this static friction between tires and the road, we have a condition that the car will stay on the road if Fc, centrifugal force, is equal to mg times sinus theta. So Fc is equal to mv squared divided by r. Here we have mg sinus theta. So we cancel out this m, and we get expression for sinus theta equal to v squared divided by r times g. So that means if we want to move along this curve trajectory, curve road, with some given velocity v, then this road should be tilted by angle theta. And in this case, just this geometry can compensate lack of friction and provide safe conditions for driving along such a road. Okay, so now let us focus on drag force. But never forget to change your tires to winter type. So with drag force, let us consider a boat. Let's see how I can draw a boat. On some water surface. And here we have axis x. So at initial moment of time, t equals 0, this boat is at coordinate x equals 0, and it moves along axis x with some initial velocity v naught. So now, what do we want to know? We want to figure out how velocity of this boat will change with time. So velocity as a function of time. So keep in mind, we don't have any propeller there attached to the boat. So it just moves by inertia. And of course, it will experience some drag force. Otherwise, if we neglect use it, it will just move without stopping forever. But it's not the case in reality, so we have some drag force. Drag force, let's consider first case when we have low velocity regime. We don't create any turbulence, and that's why the drag force is proportional linearly to the velocity. So we can write, since no other forces are exerted, like weight is compensated because of water, and we can write that MA is equal to minus K times V. So only drag force will define the acceleration of this boat, and obviously this acceleration will be negative because it slows down. So it goes from velocity v naught to eventually it will go to 0. So now let us refresh what's the definition of acceleration. It's first derivative of velocity over time. So we can write here first derivative of velocity over time, dv over dt. Now let us substitute it instead of acceleration in the equation. So it will be m, oh, it doesn't work, m times dv over dt, and that is minus k times v. Now, we separate variables, so we have velocity-related terms in the left side and time-related terms in the right side. So we get dv over dt, sorry, not dt, over v. And that is equal to minus k over m times dt. Okay, is it clear? We just move it separately. Now it's actually a very simple differential equation which can be solved by simple separation of variables. So now we can integrate left and right side and get the solution for this differential equation, because the solution of this differential equation will be our function velocity as a function of time. So we can integrate here, and k and m, these parameters do not change over time, so we integrate here. So we can take these constants out of the integral. So the left integral will give us natural logarithm of velocity. That is equal to minus k over m times t, you're right, and we need to add some constant, c1, because that is integration constant since we have not defined integral. So now the question, how we define this constant? In order to define this constant, we need to use our boundary conditions. So because constant comes from this moment when we need to give more information about the system in some specific moment of time. And based on that, we can determine constant and eventually get analytical solution of this differential equation. So at t equals 0, we have v equals v naught. So now we can write here natural logarithm of v naught is equal to minus k over m times 0 and plus c1. So here we get 0, and we see that c1 is equal to natural logarithm of v naught. Now we substitute it here and move it to the left side. So it will be natural logarithm v minus natural logarithm v naught. That is equal to minus k over m times t. So what is the property of logarithm? How we can rewrite this left side? Yes, so the difference of logarithm is equal to logarithm of the ratio. And we have natural logarithm v over v naught equals to minus k over mt. And now we want to get rid of this natural logarithm, so we use exponential function. So we can rewrite this as v over v naught equal to exponent minus k m times t. So from here, velocity as a function of time is v naught times exponent minus k over m times t. So this is the solution, and we now see that velocity of this ball will exponentially decay over time. That's quite rapid decay, it's a very strong function. And how fast actually it decays, it will be determined by these coefficients. proper coefficient for drag force, proportionality coefficient for drag force. We'll define the surface of the uh, boat and properties of the water, viscosity and density, and also mass of the boat. So these two parameters will be very influential because they are inside this exponential function. Now let us see if we can go one step further, and from time dependence of velocity, we can go to time dependence of the position of this ball, how it travels along axis x, as its position along axis x as a function of time. So we have expression for velocity as a function of time, and that can be written as first derivative of position over time. So we can write now, again, separate these variables, position to the left and time to the right. We will get dx equal to v naught times exponent minus k over m times t and times dt. So now we need to integrate it again in order to get position as a function of time. So here we have integral, and here, because v naught is a constant. So in the left side, it's quite simple. So we have x. Also, don't forget about constant. Let's have some c2. And here with this integral. So in order to take this integral, we need to have differentials the same as argument of the exponent. So what we need to do, we need to multiply it by minus m divided by k. So then it will be exponent minus k divided by m times t. And here will be d, not dt, but it will be d minus k over m times t. So now you see that differential here is the same as argument of the exponent, and that means we can apply this simple rule, exponent of integral of exponent of x dx is equal to exponent x. Instead of x is our expression here. So that will be equal to, sorry, we need to multiply here because looks like it's minus. So it will be minus v naught times m divided by k. And this integral will give us exponent minus k over m times t. So again, we have this constant c2. We need to determine it. So we determine this constant from boundary conditions also. And we remember, if we look here, that at t equals 0, position x is equal to 0. So we come back here and substitute this condition. So we have 0 instead of x plus c2. That is equal to minus v naught times m divided by k, and we need to multiply by exponent minus k over m times 0. So exponent in the power of 0 gives us unity. So this is unity. So this will be actually equal to minus v naught times m divided by k. From here, we see that c2 is equal to minus v naught times m divided by k. Now we substituted this expression for C2. It doesn't look like this, like here. So we get x, not plus but minus, v naught times m divided by k, and that is equal to this part, minus v naught times m divided by k times exponent minus k over m times t. So now we move this part to the left, and we already can express position as a function of time. That will be equal to v naught times m divided by k minus v naught times m divided by k times exponent minus k over m times t. We see that these guys are the same, so we can take them out of parentheses. So it will be v naught times m divided by k, unity minus exponent in the power minus k over m times t, and we close this parenthesis also here. So this, let me clean it a bit so it will be like this. So this is the solution for position of this boat as a function of time. And now we actually can consider some time approaching to infinity. But for sure, during this time, boat should stop. So in this case, we see that this exponent is approaching to 0 because it's in the power of minus t. So exponent approaches to 0. And then x maximum, it will be the distance this boat will move until it stops, will be equal to v naught times m divided by k. So the larger initial velocity and mass of the boat, the further it will move until it stops. And of course, the larger proportionality coefficient for drag force, it will slow down this boat faster, so it will move to along shorter distance.